How's it going, electricity guys and girls? All right, so we're going to talk a little bit more about series circuits, parallel circuits, and the new one is the combination of the two called a series parallel. So first, we're just going to review series circuit with you so we have understanding before we move forward, and we'll take it from there. So our series circuit. All right, so we got to think about what makes a series circuit. And quick little review for us. Our series circuit, I'll draw it out real quick for you. Got our power supply. And our series circuit is the key here. It's got only one path for electricity to flow. And that's what makes a series circuit a series circuit. So I got this cool little template here I'm trying out. And I'm drawing, instead of the loads that we normally see, I'm actually drawing resistors. Everything that we've been doing in class has been a resistive circuit. So I draw a resistor, and you're used to seeing that little L with the circle in it. Before in the past, we've always drawn that L. Same thing. This is a resistive load. This is a resistive load. We're just actually giving you now the symbol for an actual resistor. Okay, and we'll get into that further along as we go. So remember, when we're calculating for resistance in a series circuit like this one, everything does have that value. So if this was R, we'll call it R1 equals 10 ohms. This is R2 equals 10 ohms. In the total resistance in a series circuit is equal to the sum of all the resistance in the circuit. So this one's an easy one, right? So RT, which would be total resistance of the circuit, equals 10 ohms plus 10 ohms. And that gives us our 20 ohms of resistance total for the circuit. So that's our review of our series circuit. Current is constant in the series circuit. So if I had, let's just say 2 amps of current flowing through this particular circuit, that would be a consistent 2 amps of current flowing through each load or each resistor in this particular circuit. The sum of the voltage drops across all resistors must be equal to the source of the voltage. So if we have voltage drop across here, we do a little Ohm's law real quick. E, I, R. And I don't know what E is. I cover that up. We got I times R. RT is 20 times I. 2 times 20 equals 40. So 40 what? The voltage of this circuit equals 40 volts, okay? So given the voltage of the circuit is 40 volts, we know that the resistance will decrease across this. Given that both resistors are the exact same value, this one's easy. So the voltage drop across this would be 20 volts. The voltage drop across this particular would be 20 volts as well, okay? So that's just a review. Using a little bit of Ohm's law here, our series circuit, just understanding about the voltage drop in a series circuit, the current in a series circuit, and resistance in a series circuit. So we're going to go ahead. We're just going to review real quick. We're going to do that parallel circuit. And remember, the rules are slightly different. The parallel circuit, no big deal. Quick review with you guys. And what makes a parallel circuit a parallel circuit? The key word here is more than one path, okay? I guess it's a bunch of words, but you know what I'm talking about. So I'm going to draw that parallel circuit for you. And I'm just going to go ahead and draw in our power supply, which happens to be a battery. There's little cells of battery we're drawing here. And I'm going to draw you folks a very basic parallel circuit. But once again, we're just using these resistors in place of the load, just to get you a little more comfortable seeing that in a circuit. And remember, that means the exact same thing as the loads that we have been drawing in the circuit so far, okay? So we talked about this being a parallel circuit. Why is this a parallel circuit? Remember, the spelling's terrible, not an English teacher. You got more than one path. I put my finger in the power supply, drive the car around. If I have more than one path, I've got two options here. Go down this road or I can go down this road here. We know that this is going to be a parallel circuit because of that fact that there's more than one path. Some notes on that. Total resistance is nasty in this. We don't do that very often in intro class, but if I'm going to give you the R1 value is 10, the R2 value is 10 ohms again, we do have to remember, and this is just a kind of little bit of a note here, that the total resistance is less than the smallest individual resistance in the circuit. So we know that the total resistance of this particular circuit will be smaller than the smallest value. So we know that the total resistance is going to be smaller than 10 ohms. And there's an equation for that, which I said we don't really get into too much in this intro, but just so you have it in front of you to understand what it looks like, we got 1 divided by, and then we go 1 divided by R1 plus 1 divided by R2, and that would give us our answer for this particular problem. You can do the math on your own. I'm not going to bore you with that, okay? So that's our resistance in a parallel circuit. When you're dealing with the currents through a parallel circuit, they equal, this is Kirchhoff's law here, so if I have, let's just say we'll go 2 amps again of current flowing through it, 2 amps of current, you're going to have that current 2 amps flowing through the circuit. And then when it gets to that split here, the current will divide between the 2 loads here. So if you just, for example, say we have 1 amp of current flowing through, each one of these, they'll join back up again. You'll have 2 amps flowing through the circuit, and then it will break off and divide between the 2 and then combine back together to get the 2 amps on the way back home again. So that's our current in a parallel circuit. Voltage, it's the easiest one we got out there. So if you have a voltage total, so let's go again, let's just say this is 40 volts total, we know that in a parallel circuit, the voltage is going to be the same across both values here. So this would be same 40 volts again. That's really the biggest difference between series and parallel. In series, if you remember, we were dividing that voltage up as they pass through each resistor, but because we have multiple paths for electricity to flow, you're going to see that voltage stay the same throughout each load in the circuit. So if we added a bunch of lights on this or resistance values here, you'd still see that 40 volts all the way across throughout. That's taken care of. Now, here comes the rig world. Now we're talking about our series parallel circuits. And don't get scared on me. It's not that bad. Why? Because really what we're trying to do is break down a series parallel circuit into a series or a parallel circuit. So it's really just taking the basic stuff we just learned, and we're just applying it multiple times throughout the circuit. So I'm going to go ahead and I'm going to draw you guys and girls another circuit, but this time we're going to go with that series and parallel just to give you a better idea of what that's going to look like. And I'm going to go ahead and I'm going to put a couple different loads in this particular circuit, like so. Okay, here's a series part of the circuit where we got only one path for electricity to flow through these particular 3 resistors here. And this guy here, this resistor is in parallel with these 2. So when you're starting off with a series parallel circuit, what is the rule of thumb here to remember is that when you're working with a parallel circuit, you keep breaking down the circuit from series to parallel, series to parallel. So we're actually trying to make this series into one resistor. That's what that means, right? So we're actually going to take the values. I'm just going to give you guys these R1, R2, R3, R4. So R2, R3, and R4, really what we're trying to do is combine these 3 separate loads into one load. So we're going to take this part of the circuit, which is a series circuit, and we're going to turn it into one single resistance value. That will help us out when we're doing our Ohm's law calculations. Okay, so for example, if we had a resistance value here of 5 ohms, this one is 5 ohms, this one is 5 ohms, all we need to do is add these 3 up, and that would give us 15 ohms. So if I were to redraw the circuit, I think you guys will understand where I'm getting at here. I'm going to try to draw everything lined up again, make it easier to visualize. I love that template. It's nice. This here is a combination of R2, R3, and R4. So this would become 15 ohms. And this is R1 plus R2 plus, R2 plus R3 plus R4. And that will give us a parallel circuit. All right, so this breaks this back down to a parallel circuit. If I gave this a 5 ohm value, gave this a 5 ohm value, then we do that little more complicated equation to give us the RT in a parallel circuit, which is that 1 over, we can call this R1 again. And that is that combination of all of them, right? 2 plus R3 plus R4. And those would all get added up prior to doing the math and give us the answer to that equation if you chose to do so. And like I said, this is a little more advanced than what we do in intro, but I want you to understand what that looks like in a series parallel circuit. Why do we use a series parallel circuit? When we get into control work, you're going to see lots of different loads out there in our world of electronics and electricity, and different loads will have different voltage requirements. So you can build a single circuit with a single power supply, and that power supply will be able to supply loads that have different values to them. So for example, if we go back up to the top view here, we remember when we were discussing voltage, if I had a voltage here in this circuit of, let's just go ahead and say 9 volts, that 9 volts would carry across R1, and then the combination of that 9 volts would get broken down throughout this. And these are all the same values, so in reality, that 9 volts would get broken up between 3 volts, 3 volts, 3 volts. All right, so we've got different components in here that might require a lower voltage to run and operate correctly. And you might have a component that takes the entire 9 volts of the power supply, but now we can use one power supply to apply voltage to a variety of things, even if their rated or running voltage is going to be different than that source voltage. And that's when you'll see your series and parallel circuits used in real world applications. And that's it so far.